Assalamualaikum and good day guys. In this video, we are going to explore the different types of matrices and learn how to recognize special patterns such as diagonal, scalar, zero, identity, triangular, and finally row echelon forms. Please bear in mind that all of these concepts are not just theory. They will form the foundation of solving system of equations efficiently. So with that, let us start. First, we have a diagonal matrix. Diagonal matrix is a square matrix where all elements outside the main diagonal are zero. So this is a kind of diagonal matrix where only a diagonal element have values and others are zeros. So for A here, we have one element that is in a diagonal line that is 0, so this is not a diagonal matrix. Next, scalar matrix. It is a diagonal matrix where all diagonal elements are equal. So it is actually a diagonal matrix plus this element, which is element are equal. A diagonal matrix that has an element that is equal is called a scalar matrix. And for this one, this is an example of a diagonal matrix but not a scalar matrix. And this is actually a diagonal matrix that is actually a scalar matrix. Next is zero matrix. Just like its name, it is named zero matrix because all of the elements contains of zeros, and it is always denoted by zero itself. An identity matrix, among the important metrics that you're going to use later, is often written as I. It has ones in the main diagonals. You should get it ones in the main diagonals and zeros anywhere else. Next, we have the negative matrix. The negative matrix means each element is multiplied by -1. For example, let's take a matrix A here multiplied with -1. So the negative matrix is this. Please note also that this is, even though we are talking about negative matrix now, what is actually happening here, they are performing what we call scalar multiplication, where we have a scalar value multiplied with a matrix. We're going to see further later. Next, we have triangular matrix. Alright, the name itself is called triangular because of the triangular form. Alright, because of the triangular form. So, it is called upper triangular matrix when all elements above the diagonal here, all elements including the diagonal contain a value. So basically for upper triangular, all elements below the diagonal will have 0. Okay, the other way around, for lower triangular matrix, from the diagonal and below will have a value, and for those upper value from the diagonal will contain 0. Now that we have learned about the matrix types, the next thing to do is to learn about the metric operation. So just like real number, we have the basic metric operation. So let's look at the sum and subtraction. So when you are summing the metric, you're actually summing them by element. So you are summing this element with this element and this element with this element respectively until the end. The same goes when you subtract. And for scalar multiplication, just like we discussed during the negative matrix, it's actually multiply each element with the scalar value, which is the value that you need to multiply later on. Now, other than scalar multiplication, we also have just a common multiplication between matrix. So in the multiplication between matrix, there are situations where two matrices can be multiplied or cannot be multiplied together. So let's look at this rule. Okay, so we can only multiply between two matrices when, right, the size of the matrix is as follows. So if you have matrix one matrix of m times n, alright, and another matrix of n times p. Look at the second the column for the first matrix and the row for the second matrix. It should be in the same order. If this is the condition, then we know that that matrix can be multiplied together. And we know that after we multiply these two matrices, we are going to get m times p as the new order after multiplication. That is how we actually do multiplication. So to discuss in detail on how to do all the multiplication and other operations, we can look at one example. Maybe let us try question 4e. Right, 4e. Firstly, let's rewrite the matrix in this form. So let us first substitute all the needed matrix in the equation. Now, based on the priority, we are going to solve for this first. This is a scalar multiplication where you multiply each element with 3. And this is what it becomes. Next, we need to solve the operation inside the bracket. So let's pull this matrix down. And what do we need to do now is to subtract between these two matrices. So first, before you do the subtraction or later on maybe addition, you'll need to check the size of these two matrices. Both of the size need to be the same. So this is 3 times 3. In order to do the subtraction, it also need to be 3 times 3. Unless otherwise it is not possible. So let's do the subtraction. And remember, the subtraction need to be done by element. So element 1 1 subtract with 1 1, 2 2 2 2 till the end, 3 minus 0 here. Next, we need to pull down, right, this equation A to multiply it with this, right? Okay, so before we proceed with the multiplication, let's check, make sure that it is possible for us to do the multiplication between the two matrices. So the first matrix is actually 2 times 3. The second matrix is 3 times 3. So just by looking at this, we know that they can be multiplied, and we also know that the last order of matrix that we're going to get is 2 times 3. So just to make it clear, multiplying these two will give us 2 times 3. In other words, if we try to write down the element first, this is how it should look like. So we have A11, A12, A13, A21, A22, A23. So this is how it should look like. So the next thing that we need to do is to find the value. So for A11, the way to multiply it is by multiplying between the row with this column to get A11. And then for A12, we're going to multiply this row with the same column. And then the next one will be A12. We are going to use the first row with the second column, the second row with the second column to get A22. For A13, we are going to use the first row with the last column, and A23, the second row with the last column. So basically, we need to sum all of the multiplication between row and column. So without further ado, let's do the first one. Okay, so basically for the first one, it is 2 times 3. 2 times 3 plus with 1 times 1. 1 times 1 plus negative 2 times negative 10. Negative 2 times with negative 10, which will give us 6 plus negative 6 plus 1 plus 20, so which will give us 15. So that is for A11. Alright, now let's look for A12, which is column 1, row 1 and column 2. So A12 is 27. Let's do it for until A23. Alright, and you can pause the video if you want to cross check. I will just jump to the answer. So this is it. We have A11 till the end, A23. So let's just write it down, rewrite it. Okay, so we have 2 times 3 a structure. So A11 is 15, A12 is 27, A13 is negative 28, A21 is negative 55, A22 is 42, A23 is negative 28. Alright, so this is how you calculate it. bear in mind that I might making a mistake. So one word that I can advise you is that always be careful in doing your calculation, especially for this case of multiplication, because we can make a silly mistake. It happens to me a lot of time. Okay, so that's it on the operations, right? We have actually discussed on the subtraction, right? The same with actually addition, and then scalar multiplication, and then we have here a multiplication between two matrices. Now, do you realize that we did discuss division, right? How about dividing between two matrices? Okay, so for matrix, that will be a special case because we don't have directly divide, right? Matrix divide with matrix, right? We are going to discuss that later in one topic specifically for division. Okay, so for this part, this is the end of the matrix operation. Okay, but still not the end of the video. We have a little bit more to go. Let's look at transpose of matrix. What does it mean by transpose of matrix? So basically, it is denoted as a to the power of t. T, small t here denoted as transpose. So basically, when you transpose a matrix, we actually switching between its row and column. So basically, if you look at B here, so later on if you want you to write a B transpose, just switch between the row and column. So B transpose is actually equal to, so the column here will become row, so 0 to 1, and then 1 for negative 1 will be the next rows, 1 for negative 1. Okay, so that is transpose. Now from this transpose, we can identify two things, which is symmetric matrix and skew symmetric matrix. So for symmetric matrix, we call it a symmetric matrix when the transpose of the matrix is actually equal to the matrix itself. So for example, if you try to transpose this matrix, change the column to become a row and row to become a column, it will still be in the form of the same original matrix, which is 1 2 3 2 4 5 3 5 6. It will be the same. So if that's the case, this is a symmetric matrix. And then we have a skew symmetric matrix. It is a situation where it is equal to the negative of its transpose. So this A, when you do the transpose, this is what you get. Okay, so look at the element. So 0 retain as 0, it doesn't matter, but then the positive become negative, and negative become positive, and this for these two, which is actually negative, it become positive. The positive one become negative. It's just like that, a negative matrix where you multiply each element with negative 1. So that is a skew symmetric matrix. And we have kind of the last part, right, which is a row echelon form. So this is what it called row echelon form. It talks about a form where we look at a row, and we are going to identify whether it is a form of REF, row echelon form, or not row echelon form. And the way to determine it is by looking at these properties. There are three things that need to look at to determine whether it is REF or not REF. Firstly, of course, we are going to look at rows. That's why the name is row echelon form. So any rows that contain entirely 0 occur at the bottom. So basically, if you have a row that is actually entirely 0, like this, it should be at the bottom of the matrix. It cannot be appear at the second or the first. It should be at the bottom. And then for the second one, for each row that does not contain entirely 0, we mean they have a value, the first non-zero should be 1. So for this one, it is 0, so it doesn't matter. But for those that is actually containing a non-zero, like this one, it has 3, 5. The leading value should be 1. Right? The leading value for this one, for example, should be 1. It will start with 1 at that particular row, and then we call it that leading one. So, and lastly, for each non-zero rows, the leading one appear to the right of the leading one of the previous row. What does it mean by this? The form should be in the form of stairs for the number 1. So for this one, it should be like this. So one cannot, after you have 1 at this place, you cannot have 1 before it. It should be after it. So like this one, right? So this is, even though it is exit, it's still not at this area, so it is still considered okay. The same goes for this one, right? This is actually has no value, entirely 0 at the bottom, so it is still fine. Okay, that is actually REF. So let's demonstrate our understanding on REF. So let's see. A, is it REF or not? So you have an entirely 0 row here, but it is not at the bottom, it is at the middle, so this is not REF. Then secondly, you'll see that it doesn't have entirely 0, so skip that. And then secondly, about the leading one, so for the all of the non-zero rows, you have a leading one, start with 1, start with 1, start with 1, check. And lastly, the leading one appear in the form of stairs, like I said just now, so it is actually like this. So this is actually REF. And lastly, okay, we have one non-zero that is not starting with 1, so C, it is not REF. Alright, maybe I am too fast. You can actually pause the video and try to make sense of it after this. The next one, which is the last part of the video, will be about RREF, which is the extension version of the REF. So reduced row echelon form is the REF that is actually being extended for one more properties. So what is the extended properties? It is this. So for reduced row echelon form, this is the only properties that are actually referring to the column. So the first three, right, like REF is the rows, and this one things will be looking at the column. So given that it is REF, now let's see whether it is just REF or it is actually an RREF. So how to determine it is RREF? So look at the fourth one. The column contains leading one and the entries should be 0. So we have the leading one. So look at the column of the leading one. It should be containing 0. So 1 and 0 only. So let's check of the example of REF. So basically it is REF at the first place, right? It is REF. But then look at the leading one, the column for the leading one contain. Now let's look at the example to determine RREF. So basically to make sure that it is REF, it should be REF first. So let's see, is it REF? So for all of this, right, this is REF, this is also REF, and okay, every one of each is REF, and but is it RREF? So look at the column for each leading one. If it contain none other than 0, then it is RREF. So this one is RREF. For this one, leading one here 2, so RREF. As for that, and this one is also RREF. Right, this is example of not RREF, where you have a leading one but the column contain 3, right? So basically this is non RREF, but it is actually REF. So that's it for this video. In this lesson, we explored the special types of matrices, which is diagonal, scalar, zero, identity and triangular. Remember, those are important. And the idea of transpose and how it helps to later on to define symmetric and skew symmetric matrices. And finally we talk about REF and RREF, and later this will also help us to solve equations systematically. So in the next video we are going to talk about determinants. Okay, so thank you and Assalamualaikum.